Guys, this is the Unit 3 8.4 Academic Chemistry Notes. So today we're going to be talking about the polarity of molecules, and we're going to figure out the age-old question of why oil and water do not mix. Get excited. Okay, you're going to need a few things. You're going to need your electronegativity periodic table. So if you are my student, then that is in the Unit 3 intro reading on the back. You're going to need a handy-dandy calculator. You're going to need, my students need 8.3 notes, the back, the whole Vesper molecule situation. And I highly recommend you go grab yourself a molecule building set. Not only is it fun, but it'll help you visualize what we're talking about. All right, let's get started. So, first of all, let's review. A dipole is seen when bonded atoms have an electronegativity difference of greater than 0.4. So this means that there's a partially positive pole and a partially negative pole, and pole just means region within that bond. And since there's two poles, it's a dipole. Get it? Dipole. Di means two. Okay. So let's just look over again what a polar bond and a nonpolar bond. They're both sharing electrons, so they're both covalent. A polar bond pulls electrons towards one side, and the side that it pulls towards makes it slightly negative. A nonpolar, they just share equally, so the electrons are seen smack dab in the center of that bond. Now, if there's only one bonding region within the molecule, as in if there's two atoms total, like HCl or H2, then the type of bond determines if the whole molecule is polar or not polar. So HCl, since it has a polar bond, the whole thing is polar. Because if this is the whole molecule and the electrons are found over here by chlorine, then the overall thing has an area of negativeness and an area of positiveness. Versus this is H2, where the electrons are right in the center, so the overall thing is equally dispersed, so the whole thing is equally dispersed. Well, what happens if there's more than two atoms? Okay, let's talk about what a nonpolar molecule is. So we just saw an example, H2, but what about things that have more than two atoms? So in a nonpolar molecule, electrons are shared equally across the molecule. They do not have any partial charges in the molecule, so everything is hunky-dory the same. And if you look at CH4, methane or fart gas, and we look at this middle picture, so this middle picture shows the electron density, and if you notice, the whole thing's pretty much the same color. There's a little shading just to show curves, but it's the same color, meaning the electrons are shared equally throughout, so the whole thing is nonpolar. There's no pull of electrons or no poles to make partial negative, partial positive charges. And the overall thing is neutral because it is a covalent molecule. Whenever you touch molecules, none of them shock you, like there's no electric charge that you get. So methane or fart gas, it's not going to shock you if you touch it because there's no electric charge. Nonpolar molecules are hydrophobic. Hydro means water, and phobic, you generally think of like a phobia, like a fear, like arachnophobia is scared of arachnoids or spiders. But for this, since molecules don't have fear, it's hating or dislike. So hydrophobic or nonpolar things don't like water because water is polar, and so nonpolar things are going to repel from it. So like dissolves like. Polar stuff dissolves in polar stuff, nonpolar stuff dissolves in nonpolar stuff. The two don't mix. Oil and water don't mix because oil is nonpolar. So it is hydrophobic, it repels water. So what properties make a molecule nonpolar? The first idea that would make something nonpolar is if all the bonds in the molecule are nonpolar and there's no lone pairs on the central atom. So an example of this is BH3. So if I draw BH3, it looks like that. Here is the molecule. And if you notice the difference in electronegativity between boron, which on your periodic table of electronegativity is 2.0, and hydrogen, which is 2.1, the difference is only 0.1. So that's very, very small. These electrons are shared evenly throughout, so there's no overall pull of electrons. So this is nonpolar because there's no pull on the electron. Another way that makes something nonpolar is if bonds are polar. Okay, whoa. Bonds are polar. I just want to point that out. You can have a molecule that is overall nonpolar even if bonds are polar. All right, let's discuss why. but they're equally dispersed or they're symmetrical and therefore they cancel out. So boron trifluoride, very similar to what we had before, but now we have fluorines here, which have a very strong pull. So our electrons are being pulled out in all directions. And since they're being pulled out in all directions, that pull cancels. So we have dipoles within, but because they're all pulling out, they cancel each other, right? If you play tug of war and pull it in either direction, you don't move either way. Same happens to your overall, so these dipoles all cancel because they're all symmetric along one point in the center. So there's no overall dipole, nonpolar. This happens for any of these type of molecules. So when you have 0 lone pairs, and it's the same on either side or all sides of your central atom. So since these are all fluorines, then the dipoles are all the same size, so they cancel out. Okay, so polar molecules. What makes something polar? In polar molecules, electrons are shared unequally across the molecule, thus creating a slight positive and slight negative end on the molecule. So water is our example. There is this overall negative charge a little bit over here and partially positive over here. If you look at our picture of electron density, you can see this red area is the electron density around oxygen, and down here, this blue area is the electron deficient area of hydrogen. Still, it's an overall neutral molecule. If you put your hand in a glass of water, water is a polar molecule, you don't get electrically shocked. So overall, still neutral. And it's hydrophilic, meaning water loving. Philic means loving because water is polar and like dissolves like. So polar molecules dissolve in polar solvents. So what makes a molecule polar? If the dipoles don't cancel because of asymmetry, as in not symmetrical. So here's my molecule for CClH3. I've got a carbon in the center, a chlorine up top, and then 3 hydrogens all around it. And here's how I draw it on the paper. And I've added the electronegativity. So carbon has a 2.5 electronegativity, hydrogen has 2.1, chlorine has 3.0. So all of these bonds are relatively equal, but it's the direction that matters. So notice it always points to the more electronegative. So overall, the pull is going up. So this is what you need to draw. The overall dipole moment in this molecule is going towards the chlorine because all the electrons are getting pulled that way. And because of that, there's an area of electron deficiency. So there's a partial positive area down here by the hydrogens, and there's a partial negative up here by the chlorine. So that's why this is polar, because there's an overall dipole. Those dipoles do not cancel because they're not going in opposite directions. Another example of what makes something polar is lone pairs push the geometry so that dipoles are unable to cancel out, even if you have equal dipoles. The lone pairs make the molecule asymmetrical, and you'll notice the word asymmetrical comes up a lot for polar. So polar things are very asymmetrical when it comes to dipoles. So for example, water. So here's my water molecule, and I've put in the lone pairs here, and I'll add them like that. Let's just take them out for now, though, on the model. So if you look at this, although there is a dipole going here, there's also a huge amount of negativeness up here from my electrons. So if I look at the overall direction of electron movement, it's going to overall come up here because not only is it coming up from the hydrogens, but there's also a bunch of just negative electrons up here. Although these two dipoles are the same, they're not going in opposite directions, right? They're both going, if you look at this again, they're both going somewhat up. So overall, it goes up. So there is a dipole. On the top here has an area of slight negativity. Down here by the hydrogens, slight positivity, and that's what makes this polar. When the bonds are nonpolar, okay, you would think the whole molecule would be nonpolar, right? But if there's a lone pair or multiple pairs, that causes a strong concentration of electrons in the molecule. So nitrogen trichloride, it looks a bit like this. So here is my structure. And although nitrogen and chlorine have the same electronegativity, so right here in this bond, there's no overall pull of electrons. However, up top here, There's a whole area of electrons. That's all there is on top. It's just a lone pair right here. So even though there's no dipole here, overall there's a pull of electrons towards this top because this top region legit just has electrons. Like that's all that's there. So that's a partial negative charge up there, which then ends up making this partially positive. So this molecule is polar because of the lone pair of electrons. Okay, so now it's your turn. I'm going to give you a list of molecules, and you're going to figure out if overall the structure is polar. So I'm not just talking about the bonds, I'm talking about the whole thing. So here are the three molecules that you are working with: phosphorus pentachloride, hydrosulfuric acid, or H2S, and carbon tetrafluoride. So what you're going to do is you are going to freeze the video, and I know some of you guys are opposed to that, but you literally need to pause the video, do the work, and then come back and check and see if you're right. That way you can get some questions answered before it's on a graded worksheet. Okay, so pause your video, and we'll be back in a second to discuss. All right, so phosphorus pentachloride looks like this. So you want to figure out the bonds. So the bonds are polar bonds. However, it's a trigonal bipyramid shape, which is the zero lone pairs category. So it is symmetrical. So the dipoles will cancel, and overall the molecule is nonpolar. H2S looks like this. Although they are polar bonds on the bottom, they do not cancel because it is angular or bent, has a bent shape, which is asymmetrical. The dipoles do not cancel, so H2S is a polar molecule. Carbon tetrafluoride looks like this. So they each have polar bonds. It is a tetrahedral shape, which is in that zero lone pair category. So it is symmetrical all the way across since all the bonds are equal. And so the dipoles cancel, and overall this is a non-polar molecule. All right, best of luck with polar molecules or non-polar molecules. Make sure you talk to me if you have any questions. Otherwise, I'll see you in the next set of notes.